The control room at the Harvard Center for Astrophysics fell silent at 3:47 a.m. on October 10th, 2025. The spectroscopic data had been refreshing on multiple screens for 6 minutes, displaying numbers that refused to make sense, no matter how many times the instruments recalibrated themselves. The readings weren't supposed to look like this. Nothing about 3I Atlas was supposed to look like this. For 3 months, astronomers worldwide had been calling it a comet. The designation said comet. The outgassing looked like comet behavior. The tail structure, while unusual, still fell within the broad category of things comets do when they warm up near the sun. Every press release, every scientific paper, every casual conversation among colleagues assumed we were tracking an interstellar comet, just like 2I Borisov before it. Rare, yes. Exciting, absolutely. But fundamentally understood. The JWST spectroscopic data that arrived that October morning destroyed that comfortable assumption in under 3 seconds. The comparison files showed what comet spectra should look like at this distance from the sun. Water ice signatures at specific wavelengths. Carbon dioxide absorption lines following predictable patterns. Dust particles scattering light in characteristic ways. That astronomers had catalogued from hundreds of comets over decades of observation. 3I Atlas matched none of it. The molecular emission lines appeared in completely wrong intensities. The ratios between different compounds violated every formation model for icy bodies. Most disturbing was what the spectrum wasn't showing. The silicate dust features that define comet composition were either absent or so drastically altered that they suggested material processing at temperatures and pressures that shouldn't exist in any known comet formation environment. The water signature itself posed an immediate problem. Spectroscopic analysis revealed water molecules, yes, but bonded in configurations that don't occur in natural ice. The hydrogen to deuterium ratio fell outside any measurement ever recorded from solar system comets or interstellar ice clouds. Either this object formed under conditions completely alien to our understanding of stellar nebulae, or the water itself had been altered by processes we couldn't identify. Then there was the carbon problem. The spectrum showed complex organic molecules far more intricate than comets typically display. Not just simple carbon chains or basic amino acids, but ring structures and branching compounds that suggested either extreme age under specific conditions or active chemical processing during the object's journey through interstellar space. Natural chemistry produces these molecules, but not in these proportions, not in these combinations. Most puzzling was the complete absence of certain expected compounds. Where were the cyanide signatures? Where were the formaldehyde lines that show up in virtually every active comet? The spectrum had holes where standard chemistry said there should be peaks, and peaks where conventional wisdom expected nothing. The first images of 3I Atlas arrived on July 1st, 2025, captured by the Atlas Survey Telescope in Chile. At the time, it looked like exactly what astronomers expected to find: a fuzzy dot moving against the background stars, with a faint tail developing as it approached the inner solar system. The preliminary classification went through without question. Interstellar comet. Third confirmed visitor from beyond our solar system. Exciting, but not revolutionary. Looking back at those early observations now reveals how quickly assumptions shaped interpretation. The initial brightness measurements showed an object producing a visible coma, the cloud of gas and dust that surrounds active comets. Standard procedure said to calculate mass based on outgassing rates and observed acceleration from the rocket effect. When those calculations kept producing uncomfortably large mass estimates, the natural response was to assume the measurements needed refinement, not that the entire classification was wrong. Hubble captured detailed images on July 21st, revealing the distinctive teardrop shape that everyone interpreted as a dust tail being shaped by solar wind. The anti-solar component, that unusual forward glow pointing toward the sun, raised some eyebrows, but fell within the range of documented comet behavior. Comets sometimes produce anti-tails when Earth's viewing angle passes through their orbital plane. Unusual, yes. Unprecedented, no. The images went into the database, labeled as interesting comet morphology. By August 27th, Gemini South observations showed the forward glow intensifying rather than fading. That should have triggered deeper investigation, but confirmation bias is a powerful force. The brightening got explained away as viewing geometry effects or unusual dust grain properties. Every anomaly found a comfortable explanation that preserved the comet hypothesis. Science moves carefully, which is usually wisdom, but sometimes careful becomes complacent. The JWST observations on August 6th provided the most detailed chemical analysis ever performed on an interstellar object. The initial reports focused on the high carbon dioxide to water ratio, presenting it as an interesting data point about formation conditions in alien solar systems. The full spectroscopic dataset sat in archives waiting for detailed analysis, while headlines celebrated the successful observation of an interstellar comet's chemical composition. Nobody was looking for reasons to question the fundamental classification. 4 months of observations, hundreds of professional and amateur astronomers contributing data, thousands of images and spectra, building a comprehensive portrait of 3I Atlas. Every piece of evidence got filtered through the assumption that we were studying a comet. The orbital mechanics teams modeled it as a comet. The chemistry groups compared it to other comets. The morphology analysis used comet behavior as the baseline for understanding surface activity. The breakthrough came from doing the one thing science often resists, throwing out the assumptions and starting over. When researchers finally analyzed the complete dataset without presupposing comet classification, the contradictions became impossible to ignore. The evidence had been there all along. We just weren't ready to see what it was actually telling us. The shape of 3I Atlas defies every model we have for how comet comas should behave. Standard comet morphology follows predictable patterns refined over centuries of observation. Gas sublimates from the nucleus surface, carrying dust particles outward. Solar wind and radiation pressure shape this material into the classic tail structure, pointing away from the sun. The physics is straightforward, testable, and has been confirmed thousands of times across every comet we've studied, until now. The teardrop cocoon surrounding 3I Atlas presents immediate problems. High-resolution imaging reveals a boundary layer, a distinct edge to the coma that shouldn't exist. Natural gas expansion creates diffuse, gradually fading structures. There's no mechanism in comet physics that produces sharp boundaries. The envelope around 3I Atlas looks less like escaping gas and more like something being contained, as if the visible material is being held in place rather than flowing freely into space. The anti-solar tail compounds the mystery. While comets occasionally display forward-pointing features due to viewing geometry, those are optical illusions created by dust particles along our line of sight. The glow ahead of 3I Atlas is real material, genuinely positioned between the object and the Sun. Spectroscopic measurements confirm active gas emission in the forward direction, not reflected light or geometric tricks. Something is pushing or pulling material sunward against every force that should be driving it away. Even more puzzling is how the morphology changes over time. Normal comet tails respond dynamically to solar wind variations and the comet's rotation. They flutter, they stream, they show turbulent structures that reveal complex gas dynamics. 3I Atlas maintains an almost static configuration. The boundary layer stays remarkably stable. The anti-solar component grows steadily, without the fluctuations that characterize natural outgassing. It's like watching a fountain that never wavers, despite changing wind conditions. Close examination of the dust distribution reveals additional anomalies. Comet dust follows ballistic trajectories modified by radiation pressure. Larger particles fall closer to the nucleus. Smaller particles get pushed farther out, creating predictable size sorting patterns. The dust around 3I Atlas doesn't follow these rules. Particle size distribution appears uniform across the entire coma. Material that should have been blown away by solar pressure remains close to the central body. Material that should have settled nearby extends unexpectedly far from the nucleus. The rotation problem adds another layer of strangeness. Comet nuclei tumble chaotically, their irregular shapes and active jets creating complex rotational dynamics that show up as periodic brightness variations. Light curve analysis of 3I Atlas shows variations so subtle they barely register above measurement noise. Either this object has perfectly uniform surface activity, which nature essentially never produces, or the visible coma isn't responding to nuclear rotation the way it should. Attempts to model the observed morphology using standard comet physics have failed completely. Every simulation produces structures that look nothing like what telescopes actually see. The shape of 3I Atlas is telling us something fundamental about its nature, and that message is clear. Whatever this object is, it doesn't behave like a comet. The comet hypothesis rests on three fundamental pillars. First, visible outgassing activity that creates the characteristic coma and tail. Second, a corresponding rocket effect, where escaping gas creates measurable thrust that alters the object's trajectory. Third, a correlation between activity level and distance from the Sun as solar heating drives ice sublimation. 3I Atlas violates every single one of these principles in ways that make the comet classification untenable. Start with the rocket effect, the most damaging evidence against comet classification. When gas escapes from a comet's surface, conservation of momentum requires the nucleus to recoil in the opposite direction. We've measured this effect on hundreds of comets with exquisite precision. The acceleration is small but absolutely measurable, typically around 10 to the negative 8 meters per second squared for active comets at this distance from the Sun. 3I Atlas shows acceleration below 10 to the negative 9 meters per second squared, more than 10 times weaker than it should be. The only way to reconcile visible outgassing with negligible rocket effect is enormous mass. The preliminary estimates suggesting 33 trillion kilograms weren't errors or exaggerations. They were the minimum values needed to explain the observations under comet physics. But that creates an impossible situation. an object that massive made of normal comet material, ice and rock mixed together, would require a nucleus at least 5 kilometers across. Detailed imaging shows no nucleus anywhere near that large. The central condensation, visible in high-resolution images, measures perhaps a few hundred meters at most. The mass discrepancy forces an uncomfortable choice. Either 3I Atlas has density values completely unlike any known comet, more than 10 times denser than water ice, or the visible activity isn't producing the thrust it should. Both options break the comet model. Comets are rubble piles, loosely bound aggregates of ice and dust with densities well under 2 grams per cubic centimeter. Dense objects require compression and heat, conditions that destroy ice. And if the outgassing isn't producing thrust, then the gas isn't actually escaping, which contradicts everything we observe about the expanding coma. The activity pattern provides the final blow to comet classification. Comets brighten predictably as they approach the Sun, their sublimation rates increasing exponentially with temperature. 3I Atlas brightened on schedule initially, supporting the comet hypothesis through July and August. Then, in September, as it continued moving sunward into regions of higher solar flux, the brightening curve flattened. Activity levels stabilized rather than accelerating. By early October, brightness had actually begun decreasing, despite the object moving closer to peak solar heating. This inverted activity curve has no precedent in comet science. Every physical model for ice sublimation predicts accelerating activity as temperature rises. The only explanations involve either exotic ice phases with reversed temperature dependencies, which laboratory physics says don't exist, or a mechanism actively regulating surface activity independent of solar heating. Neither scenario supports calling 3I Atlas a comet. We're observing something that superficially resembles comet behavior while violating the underlying physics that defines what comets actually are. The density measurements coming back from 3I Atlas make no physical sense within any framework we currently understand. Density is straightforward physics, mass divided by volume. Get good measurements of both values, and you learn what an object is made of. Ice has a density around 0.9 grams per cubic centimeter. Rock ranges from 2 to 3. Iron pushes up toward 8. These are fundamental material properties that don't change. 3I Atlas appears to violate this basic relationship between composition and density. The mass estimates keep converging on values above 30 trillion kilograms, no matter which analytical method gets applied. Astrometry tracking shows the gravitational influence on dust particles leaving the object. Spectroscopic measurements of outflow rates combined with the absence of rocket effect. Light curve modeling of how the object's brightness responds to solar heating. Every independent approach points toward the same uncomfortably large mass range. The error bars are substantial, but even the lower bounds exceed what any reasonable comet should weigh. Volume measurements present the opposite problem. The highest resolution images from Hubble and ground-based adaptive optics systems reveal a central nucleus measuring somewhere between 200 and 400 meters across. Even being generous with uncertainties about irregular shape and partial obscuration by the coma, the volume can't exceed a few tens of millions of cubic meters. Divide the minimum mass by the maximum volume, and the density calculation returns values above 4 grams per cubic centimeter. That density puts 3I Atlas somewhere between solid rock and iron meteorites. But objects made of rock and iron don't produce the visible gas emissions we're observing. They don't develop comas. They don't show spectroscopic signatures of water vapor and carbon dioxide sublimation. Dense materials require formation under high pressure and temperature, conditions that drive off volatile compounds completely. An iron-rich asteroid might outgas briefly from surface ice deposits, but sustained activity over months demands a substantial reservoir of frozen volatiles mixed throughout the interior. High density and high volatile content are mutually exclusive properties. The density paradox forces consideration of exotic scenarios that sound more like science fiction than science. Could the interior contain massive voids, empty chambers that reduce average density while concentrating mass in dense shells? That would require structural strength far exceeding what ice and rock can provide. Could the object be made of materials with unusual properties, perhaps exotic ices that remain stable at higher densities than water ice? Laboratory physics has never produced such substances. Could we be measuring the mass wrong, or the size wrong, or both? The independent verification from multiple observatories makes systematic error increasingly unlikely. Some researchers have quietly begun discussing whether 3I Atlas might have a metallic core, a remnant planetary fragment with a thin, volatile-rich coating, producing the observed outgassing. That would explain the high density, but creates new problems. How does a planetary core travel between star systems? What ejection mechanism could launch such an object at interstellar velocities? Why would it arrive now, during humanity's brief window of astronomical capability? The density paradox trades one mystery for half a dozen new ones. The surface features visible on 3I Atlas contradict everything we know about objects that have survived millions or billions of years in interstellar space. When astronomers finally managed to resolve surface details through advanced image processing techniques, combining data from multiple telescopes, they found structures that have no business existing on an ancient cosmic wanderer. The implications are staggering. Interstellar space is not empty. It's filled with dust grains, hydrogen atoms, and high-energy cosmic rays that sandblast any object moving through them at tens of kilometers per second. Over geological timescales, this erosion should smooth surfaces into rounded, weathered shapes. Impact craters from interstellar dust collisions should pepper the landscape. The surface should tell a story of violent cosmic weathering spanning eons. 3I Atlas shows none of this expected damage. High-resolution imaging reveals what can only be described as geometric regularities. The surface displays linear features, straight edges that extend for dozens of meters before terminating at precise angles. Natural erosion doesn't create straight lines. Cosmic impacts don't produce regular patterns. These features look less like geological formations and more like constructed boundaries. Though saying that out loud invites immediate skepticism from the scientific community. Even more puzzling is the apparent freshness of the surface. Spectroscopic analysis of reflected sunlight indicates material properties consistent with recent exposure to space, not the radiation-darkened crust that should accumulate over millions of years of interstellar travel. The surface albedo, its reflectivity, measures higher than any known ancient asteroid or comet nucleus. It's as if the outer layers were somehow renewed or protected during the long journey between stars. The crater deficit presents another profound mystery. Statistical models predict that any object travelling through interstellar space for even a few million years should accumulate thousands of microcrater impacts from dust grain collisions. Surveys of long-duration spacecraft in our own solar system show this microcratering clearly. 3. iAtlas displays virtually no impact features at the resolution limits of our best telescopes. Either it's extraordinarily young in cosmic terms, or something has been resurfacing or repairing the exterior continuously during its journey. Temperature mapping reveals surface thermal properties that don't match any catalogued material. The way the surface absorbs and re-radiates solar heat suggests layered composition with distinct thermal zones. Natural rock and ice mixtures create gradual thermal transitions. 3. iAtlas shows sharp boundaries between regions of different thermal behavior, suggesting either compositional discontinuities or active thermal regulation from below the surface. Perhaps most unsettling is what looks like differential weathering. Some surface regions show the expected darkening and texture changes from space exposure. Others appear pristine, as if recently exposed or somehow protected. The pattern of weathered versus fresh surface doesn't correlate with expected exposure to the sun or interstellar medium. It looks random or possibly deliberate, but certainly not natural. The surface of 3 iAtlas is telling us a story that doesn't fit any narrative we've written before about interstellar objects. Every detail suggests either exotic natural processes we've never encountered or something we're not ready to seriously consider. The chemical composition of 3 iAtlas violates fundamental principles of how molecules form and survive in nature. The JWST spectroscopic data reveals molecular signatures that shouldn't exist together under any known formation scenario. Either we're witnessing chemistry that operates under rules we've never encountered, or these compounds didn't form naturally at all. Start with the isotopic ratios, the fingerprints that reveal where and how materials originated. Every region of space has characteristic isotopic signatures based on the nuclear processes that created those atoms. Comets from our solar system show isotopic patterns matching the primordial nebula that formed the Sun and planets 4.6 billion years ago. Interstellar ice clouds display different ratios, reflecting varied stellar environments. 3. iAtlas shows isotopic values that don't match anything in our catalogues. The deuterium to hydrogen ratio in the water signature falls far outside the range, measured in any solar system comet or any sampled interstellar cloud. The carbon-13 to carbon-12 ratio suggests formation in regions with neutron flux densities that shouldn't exist in normal stellar environments. The nitrogen-15 abundance points to processing through stellar nucleosynthesis cycles, yet the oxygen isotopes indicate cold molecular cloud origins. These signatures are mutually exclusive. They describe formation histories that can't all be true simultaneously. The molecular complexity presents an even deeper puzzle. Spectroscopy reveals ring-structured organic compounds, carbon-based molecules arranged in hexagonal patterns that typically require either biological processes or industrial chemistry to produce in significant quantities. Natural space chemistry does create these molecules, but in trace amounts requiring millions of years and very specific conditions. 3. iAtlas shows concentrations orders of magnitude higher than any interstellar ice sample or primitive comet. Most troubling are the compound ratios that violate thermodynamic expectations. Chemical equilibrium is fundamental physics. when molecules form in any environment, their relative abundances follow predictable patterns based on temperature, pressure, and available atoms. The ratios can tell you precisely what conditions existed during formation. 3. iAtlas displays compound ratios that correspond to multiple different formation temperatures simultaneously, some suggesting frigid outer solar system conditions below 50 Kelvin, others indicating warm inner regions above 200 Kelvin. The presence of certain molecules alongside certain others creates chemical impossibilities. Water ice and certain carbon compounds coexist on 3 iAtlas despite requiring completely different formation environments. Some detected molecules are only stable at extreme cold. Others should decompose rapidly unless maintained at higher temperatures. Finding them together is like discovering ice cubes and steam in the same container without a heat source. Then there's what's missing. Every natural comet contains cyanide compounds formed through standard interstellar chemistry. 3. iAtlas shows no cyanide signatures whatsoever. The formaldehyde that appears universally in icy bodies is absent. Common sulfur compounds that form automatically in space are missing. The chemical profile has holes where nature always puts specific molecules and peaks where natural chemistry rarely produces anything. The only scenarios that explain these observations involve either unknown natural processes operating under exotic conditions we've never theorized, or chemical processing through artificial means. Neither option fits comfortably within conventional astronomy. The chemistry of 3 iAtlas is screaming that something is fundamentally wrong with our understanding. Natural objects tumble. This is one of the most fundamental truths in astronomy. Asteroids, comets, irregular moons, every small body in space rotates chaotically unless tidal forces lock it into synchronous rotation around a parent body. The tumbling comes from formation processes, collisions, and outgassing jets that impart random torques over time. 3. iAtlas rotates with a stability that defies this fundamental principle. Light curve analysis reveals the rotation signature of any object by measuring how brightness changes as different surfaces face the observer. Irregular shapes create predictable patterns. An elongated object shows pronounced brightness variations as it spins. Bright when presenting its broadside, dim when viewed end-on. Active comets show additional complexity as jets turn on and off with rotation, their outgassing creating flickering brightness, changes superimposed on the basic geometric variations. 3. iAtlas displays a rotation period of approximately 11.3 hours, determined from careful photometry campaigns tracking brightness over multiple nights. That part is normal. What's abnormal is the amplitude of the variations. The brightness changes by less than 5% over a complete rotation cycle. That minimal variation suggests either a nearly spherical shape or a rotation axis aligned almost perfectly with our viewing angle. Neither explanation withstands scrutiny. High-resolution imaging clearly shows 3 iAtlas is not spherical. The visible nucleus appears elongated, with an aspect ratio of at least 1.5 to 1. That shape should produce brightness variations exceeding 20% as it rotates. The observed 5% variation is completely inconsistent with the visible morphology. It's like watching a football spin and seeing it maintain nearly constant brightness, a physical impossibility for passive reflection of sunlight. The rotation stability itself raises questions. Precise measurements over the 4 months since discovery show the rotation period changing by less than 1 part in 10,000. Natural tumbling objects show measurable spin-up or spin-down as internal stresses relax, or as outgassing creates torques. 3. I-Atlas spins like a precision gyroscope, maintaining period stability that suggests either perfect internal rigidity or active stabilization. Attempts to model the rotation dynamics using standard techniques have failed completely. Input the observed shape, estimate reasonable mass distribution, account for outgassing torques, and the simulations predict chaotic tumbling with period variations far exceeding what's observed. The rotation of 3 I-Atlas looks artificial, though using that word invites immediate controversy in scientific circles. The angular momentum distribution presents another puzzle. Natural objects acquire rotation through random processes that typically produce spin axes tumbling around changing orientations. 3. I-Atlas appears to rotate around a single fixed axis with remarkable stability. The orientation of that axis relative to its trajectory shows no obvious relationship to gravitational influences or solar radiation pressure. It's as if something chose this particular spin configuration deliberately. Some researchers have proposed that 3 I-Atlas might have internal structure that creates gyroscopic stability, perhaps a dense core surrounded by lighter material. That could explain the stable rotation, but requires internal differentiation that shouldn't survive interstellar travel. Others suggest the whole object might be spinning much faster than observed, with the visible coma somehow masking the true rotation. Neither explanation adequately addresses why the rotation behaves so unlike every other small body we've studied. Radio telescopes began monitoring 3 I-Atlas in early September 2025 as part of routine observation protocols for unusual solar system visitors. Nobody expected to detect anything. Natural objects don't broadcast. Comets, asteroids, and planetary fragments are electromagnetically quiet, except for passive reflection of solar radiation and occasional plasma interactions. What the radio observations revealed has created profound unease in the astronomical community. The initial detection came from the Very Large Array in New Mexico during a 6-hour observation window on September 8th. Faint radio emissions at frequencies around 1.4 GHz, barely above the noise threshold, but definitely present. The signal strength measured only a few Jansky, requiring careful filtering and multiple verification passes to confirm it wasn't instrumental artifact or background interference. Follow-up observations over subsequent nights confirmed the emission was real and coming from the location of 3 I-Atlas. Natural radio emission from solar system objects comes from specific mechanisms: thermal radiation from warm surfaces, synchrotron emission from charged particles in magnetic fields, plasma oscillations in ionized gas surrounding active comets. Each mechanism produces characteristic spectral signatures that identify the physical process. The radio emission from 3 I-Atlas matches none of these standard profiles. The spectrum shows narrow band characteristics, energy concentrated at specific frequencies, rather than spread across broad ranges like natural. Thermal emission. Analysis reveals multiple discrete frequency components separated by regular intervals. The spacing between these components follows a mathematical pattern, each frequency related to others by simple integer ratios. Natural astrophysical processes don't produce such precise frequency relationships. Plasma physics is messy. Thermal radiation is smooth. This looks structured. Time series analysis reveals additional troubling features. The emission intensity varies with a period matching the 11.3-hour rotation period determined from optical observations. That correlation could be natural, rotating surface features, modulating emission strength as they face different directions. But the modulation pattern is too clean. Natural sources show irregular flickering and chaotic variations. This signal modulates sinusoidally, rising and falling with mathematical precision as the object rotates. The most disturbing aspect is what happened during a coordinated multi-telescope campaign on September the 23rd. 3 separate radio facilities observed simultaneously to triangulate the emission source location. During that 4-hour window, the signal characteristics changed, not randomly, but in coordinated fashion across all detected frequencies. The narrow band peaks shifted to slightly different frequencies, maintaining their integer ratio relationships, but transposing to a new set of values. Then, after 17 minutes, they shifted back to the original configuration. Natural radio sources don't do this. Astronomical objects don't reconfigure their emission spectra on human timescales with mathematical precision. The frequency shifting suggests either active modulation of whatever physical process generates the emission, or the emission itself is being deliberately controlled. Neither explanation fits within conventional astrophysics. SETI protocols have been quietly applied to the radio data, searching for patterns that might indicate intentional signaling. So far, no obvious information content has been identified. The emissions don't carry modulated data in any recognizable format, but the structured nature of the frequencies and their coordinated behavior implies underlying organization that natural chaos doesn't produce. 3I Atlas is broadcasting, and nobody knows why. Infrared observations of 3I Atlas reveal temperature patterns that violate basic thermodynamics. Heat distribution across the object's surface follows no natural law we recognize. The thermal signature suggests either exotic material properties unknown to physics or active temperature management from within. Either possibility challenges everything we thought we understood about inert objects traveling through space. The fundamental principle is simple. Objects in space reach equilibrium temperature based on solar heating and radiative cooling. The sunlit side warms up, the shadowed side cools down, and the temperature gradient follows. Predictable patterns determined by thermal conductivity and rotation rate. Every asteroid, comet, and moon we've ever studied obeys these rules. 3I Atlas appears to ignore them completely. Spitzer Space telescope observations in mid-September mapped surface temperatures across the visible hemisphere. The sunward side should measure around 230 Kelvin at this distance from the Sun, assuming rock-like thermal properties. The shadowed regions should drop to perhaps 150 Kelvin. That's basic physics, confirmed on thousands of solar system objects. 3I Atlas shows hotspots, measuring 270 Kelvin in areas that should be relatively cool, and cold regions barely reaching 180 Kelvin in zones receiving direct sunlight. The temperature inversions make no sense. One particularly dramatic example shows a surface feature on the shadowed hemisphere, completely blocked from solar radiation, maintaining temperature 40 degrees higher than surrounding terrain. The only natural explanation requires internal heat sources, volcanic activity, or radioactive decay warming the surface from below. But those mechanisms should create broad thermal anomalies, not localized hotspots with sharp boundaries. The thermal map looks more like a circuit board with active and inactive components than a passive object being heated by the sun. Equally puzzling are the cold zones. Several regions receiving full solar illumination remain significantly cooler than equilibrium calculations predict. It's as if something is actively removing heat from these areas, pumping it elsewhere or radiating it away more efficiently than natural materials allow. The heat that should accumulate in sunlit regions isn't staying where physics says it must. The thermal response to changing solar distance provides more evidence of anomalous behavior. As 3I Atlas moved closer to the Sun through August and September, surface temperatures should have increased predictably following inverse square law relationships. Instead, the warming curve shows plateaus and steps, regions where temperature stabilized despite increasing solar flux. Then, in early October, some surface areas actually cooled while moving sunward, a thermodynamic impossibility for passive heating. Time-resolved thermal imaging reveals the most disturbing pattern. Temperature at specific surface locations varies on hourly timescales, independent of rotation or solar angle changes. Natural thermal inertia prevents rapid temperature swings. Rock and ice take hours to heat or cool significantly. 3I Atlas shows surface features changing temperature by tens of degrees in under 30 minutes. Response times suggesting either extremely low thermal mass or active temperature control. The infrared spectrum itself poses questions. Different materials emit thermal radiation with characteristic spectral signatures. The emission from 3I Atlas shows features that don't match any known mineral or ice composition. The spectrum suggests layered materials with distinct thermal properties, but the layer boundaries and transitions occur at scales and configurations that natural geological processes don't produce. The first interstellar visitor, Oumuamua, passed through our solar system in 2017, leaving behind more questions than answers. For 8 years, astronomers debated its unusual characteristics while hoping future visitors would provide clarity. The arrival of 3I Atlas hasn't resolved those debates. Instead, it has revealed disturbing parallels that suggest both objects might belong to a category of interstellar travelers we've been systematically misclassifying. Oumuamua displayed anomalous acceleration as it departed the solar system, a gentle push away from the Sun that couldn't be explained by gravity alone. The natural explanation invoked comet outgassing, despite the complete absence of any visible coma or tail. Critics argued that this required implausibly efficient outgassing from a surface that showed no signs of activity. The controversy never fully resolved before Oumuamua faded beyond detection range. 3I Atlas shows the inverse problem: visible outgassing that produces no measurable thrust. Different symptoms, same underlying mystery. Both objects display extreme axial ratios, elongated shapes, unlike typical asteroids or comet nuclei. Oumuamua's dimensions suggested something between 6 and 10 to 1 length to width ratio, extraordinarily cigar-shaped for a natural object. 3I Atlas, while less extreme, still shows pronounced elongation, inconsistent with gravitational equilibrium shapes. Natural bodies tend towards spherical or gently elliptical forms. Both interstellar visitors appear stretched in ways that suggest either unusual formation conditions or non-gravitational shaping processes. The rotation characteristics link the two objects in troubling ways. Oumuamua tumbled with a period around 8 hours, but showed brightness variations suggesting complex rotation around multiple axes. 3. I-Atlas rotates with suspicious stability around a single axis. Neither pattern matches the chaotic tumbling typical of small solar system bodies. One spins too complexly, the other too simply, but both deviate from natural norms in opposite directions. Thermal properties provide another point of comparison. Oumuamua reflected light in ways suggesting a surface much redder than typical asteroids, possibly indicating organic-rich composition or unusual space weathering. 3. I-Atlas shows unexpected thermal behavior and surface reflectivity, inconsistent with ancient exposure to interstellar conditions. Both objects display surface properties that don't match their presumed ages or travel histories. Most significantly, both objects arrived on trajectories that raise eyebrows when examined carefully. Oumuamua's path originated from the approximate direction of the star, Vega, though Vega wasn't in that location when Oumuamua would have been ejected millions of years ago. 3 I-Atlas approaches from a direction that doesn't obviously point back toward any nearby stellar system. Tracing both trajectories backward through galactic motion produces no clear parent star. It's as if both objects materialized from interstellar space without obvious points of origin. The size difference between the two visitors compounds the population statistics problem. Oumuamua measured perhaps 100 meters in length. 3. I-Atlas may be several kilometers across. Finding such different-sized objects in our first 3 interstellar detections suggests either we're extraordinarily lucky, or these objects are far more common than models predict. Neither explanation provides comfort. The pattern emerging from comparative analysis is clear. Both Oumuamua and 3 I-Atlas deviate from natural expectations in multiple independent ways. The specific deviations differ, but the underlying theme remains consistent. These aren't ordinary pieces of cosmic debris. They're something else entirely. The megacriometeor hypothesis offers an elegant solution to many of 3 I-Atlas's anomalies, while remaining within the boundaries of natural astrophysics. The core proposal suggests that interstellar space might harbour exotic ice phases, molecular structures formed under extreme conditions that don't exist anywhere in our solar system. If 3 I-Atlas consists of these unknown ices, many of its strange properties could emerge from chemistry we've simply never encountered before. Laboratory physics has discovered numerous phases of water ice beyond the familiar form that fills our freezers. Under different pressure and temperature combinations, water molecules arrange themselves into at least 18 distinct crystalline structures, each with unique physical properties. Ice 7 forms under extreme pressure and remains stable at room temperature. Ice 10 exists only under pressures exceeding 60 gigapascals. These exotic phases display densities, thermal conductivities, and optical properties wildly different from ordinary ice. The megacriometeor model proposes that 3 I-Atlas might contain ice phases formed in environments we've never studied, perhaps in the hearts of rogue planets ejected from their stellar systems, perhaps in the frigid depths of molecular clouds, where pressure from surrounding gas creates unusual conditions, perhaps through processes involving dark matter interactions or quantum effects at cosmic scales. These exotic ices could explain the density paradox, the thermal anomalies, and the chemical impossibilities all at once. High density suddenly makes sense if the ice isn't normal, water ice, but rather compressed phases with densities approaching rock. The thermal behavior becomes understandable if these materials have thermal properties unlike anything in our experience. The chemical signatures could reflect formation in environments with pressure and temperature combinations that produce molecular arrangements impossible in conventional settings. One hypothesis solves multiple problems simultaneously. The surface features might result from different ice phases with distinct sublimation properties. Some phases could sublime readily under solar heating, while others remain stable, creating the geometric patterns and thermal zones that look artificial but actually reflect exotic phase boundaries. The rotation stability could emerge from internal structure created during formation, crystalline arrangements that produce gyroscopic properties. Even the radio emissions might have natural explanations involving plasma interactions with unusual surface chemistry. This hypothesis is beautiful in its simplicity and scope. It requires only one assumption: that interstellar conditions can produce ice phases we haven't created in laboratories. Everything else follows naturally. The scientific community wants this explanation to be correct because it preserves the natural origin of interstellar objects while expanding our understanding of cosmic chemistry. But the megacriometeor hypothesis has fatal flaws that become apparent under scrutiny. Exotic ice phases require specific formation conditions, extreme pressure or temperature, or both. Once formed, they remain stable only within narrow ranges. Expose ice 7 to normal pressure, and it transforms back to regular ice within seconds. Move exotic phases outside their stability zones, and they revert to familiar forms. 3. I-Atlas has traveled through interstellar space for millions or billions of years, experiencing temperature variations, cosmic ray bombardment, and zero external pressure. Any exotic ices should have been transformed long ago into conventional materials. The captured dwarf planet hypothesis proposes that 3I Atlas isn't a comet at all, but rather a planetary body torn from its home system and flung into interstellar space. This scenario explains the large mass and high density while accounting for the active gas emissions through subsurface ocean chemistry. It's a natural explanation that requires no exotic physics, only violent dynamics that astronomy has documented countless times in planetary system evolution. Gravitational interactions during planetary migration can eject massive bodies into interstellar trajectories. When giant planets move inward toward their parent stars, they scatter smaller worlds like cosmic billiard balls. Computer simulations show that up to 10% of planetary systems might eject Neptune or Mars-sized bodies during their chaotic formation phases. The galaxy could be filled with wandering dwarf planets, former members of solar systems that no longer remember them. If 3I Atlas originated as a dwarf planet, its high density becomes perfectly natural. Small planets differentiate during formation, heavy elements sinking to form iron cores surrounded by rocky mantles and icy crusts. A differentiated body several kilometers across would easily match the mass estimates that seem impossible for a comet. The density paradox vanishes if we're looking at a planetary fragment rather than a fluffy ice ball. The active outgassing finds explanation in subsurface oceans. Tidal heating from the gravitational pull of a former parent planet could have maintained liquid water beneath an icy crust even after ejection. Radioactive decay in a rocky interior provides additional heat over billions of years. As 3I Atlas approaches our Sun, solar heating reaches through the outer layers, causing the subsurface ocean to vent gases through cracks in the ice. we'd observe exactly what we're seeing: sustained gas emission from an object too massive to show rocket effects. This model accounts for the chemical anomalies through aqueous chemistry. Water interacting with rock over geological timescales produces complex organic molecules. Subsurface ocean environments could generate the unusual compound ratios through chemistry operating under pressure and temperature conditions we don't normally study. The isotopic signatures might reflect water-rock interactions rather than primordial formation, reprocessing that alters the chemical fingerprints. Even the surface features make sense under this interpretation. Tectonic activity from tidal stresses or internal heat could create the geometric patterns. Cryovolcanism, ice volcanoes venting subsurface material, might explain the fresh surface regions and localized thermal anomalies. Dwarf planets like Ceres and Enceladus show similar features in our own solar system. Why not on an interstellar wanderer? The captured dwarf planet theory solves so many problems that researchers desperately want it to be true. It preserves natural origins while explaining the observations. It requires no new physics, just scaled-up versions of processes we've already documented. The astronomical community has embraced this hypothesis with relief, grateful for an explanation that doesn't invoke exotic scenarios. But this elegant solution collapses under one critical observation. Subsurface oceans require maintaining liquid water over the entire journey through interstellar space. Without a parent planet providing tidal heating, and with solar warmth absent for millions of years between star systems, any subsurface ocean should have frozen completely solid long before 3I Atlas reached our solar system. The ocean that explains the outgassing shouldn't exist anymore. The theory works perfectly, except for the inconvenient fact that it's impossible. Nobody wants to say it out loud. The possibility hangs unspoken in conference rooms and email threads, acknowledged through careful euphemisms and hypothetical framings. What if 3I Atlas isn't natural at all? What if we're looking at a technology, an artifact constructed by intelligence and sent on a journey between stars? The question sounds like science fiction, but the accumulating evidence makes it increasingly difficult to dismiss. Consider what an interstellar probe might look like to distant observers equipped only with telescopes. It wouldn't necessarily appear as a gleaming spacecraft with obvious engines and antenna arrays. Any civilization capable of interstellar travel would likely prioritize mass efficiency and radiation shielding. The result might look remarkably like what we're observing: a dense core surrounded by an envelope of lighter material, possibly deliberately designed to mimic natural objects for protection or camouflage. The mass-to-size ratio suddenly makes perfect sense under this interpretation. Technological artifacts concentrate mass into small volumes through engineering rather than natural accretion. A probe containing instruments, power sources, and structural elements could easily achieve densities exceeding 4 grams per cubic centimeter while maintaining a compact form factor. The density paradox that breaks natural explanations becomes an expected feature of constructed objects. The surface geometries transform from puzzling anomalies into exactly what we'd expect. Straight edges and regular patterns are signatures of manufacturing, not geology. The differential weathering reflects engineered surfaces with varying material properties, not random cosmic erosion. The thermal hotspots become power sources or waste heat from internal systems. The cold zones indicate thermal radiators designed to dump excess heat into space. Every feature that seemed wrong for natural objects makes sense for technology. The stable rotation pattern fits perfectly. Spacecraft use gyroscopes and thrusters to maintain precise orientation. The minimal brightness variations suggest deliberate attitude control rather than chaotic tumbling. The rotation rate itself might be optimized for scanning the surrounding environment or maintaining thermal balance. Natural objects tumble randomly. Designed objects rotate purposefully. The radio emissions shift from mysterious to obvious. Of course, a technological artifact would produce structured electromagnetic signals. The narrow band frequencies could represent internal communications, navigational beacons, or sensor systems. The frequency shifting observed during multi-telescope observations might indicate the probe reconfiguring its systems or responding to detection by our instruments. The mathematical precision of the emission pattern is exactly what technology produces. Even the chemical impossibilities find resolution. The unusual molecular signatures aren't failed natural chemistry, but rather synthetic materials, engineered compounds optimized for radiation shielding or structural strength. The isotopic anomalies reflect manufacturing processes using separated isotopes for specific purposes. The missing compounds aren't absent mysteriously, but simply weren't included because they serve no function in a designed system. The outgassing without thrust could be controlled venting, managing internal pressure or temperature through deliberate gas release calibrated to produce minimal acceleration. The activity patterns correlating with distance from the Sun might indicate solar power collection systems becoming more active as available energy increases. Every anomaly that challenged natural explanations becomes a feature of sophisticated engineering. This hypothesis solves every problem simultaneously. It explains all observations with one assumption, that we're looking at technology rather than nature. The solution is elegant, complete, and utterly terrifying in its implications. Because if 3i Atlas is artificial, then we're not alone, and someone else is watching our solar system. The most radical natural explanation proposes that 3i Atlas might be composed of matter in forms that physics predicts, but humanity has never directly observed. These exotic matter scenarios push the boundaries of known science while remaining technically possible within our current understanding of the universe. They offer alternatives to the technological hypothesis without invoking intelligence, though the physics involved sounds equally extraordinary. Dark matter comprises approximately 85% of all matter in the universe. Yet, we've never isolated a single particle of it in laboratories. We know it exists only through gravitational effects on visible matter and light. Standard models assume dark matter doesn't interact with normal matter except through gravity. But what if that assumption is wrong? What if rare dark matter particles can occasionally bind with normal atoms under specific conditions, creating hybrid structures with properties unlike anything in our experience? A dark matter composite object could explain the density paradox through mass we simply cannot detect directly. The visible nucleus might represent only a small fraction of the total mass, with the bulk existing in dark matter components that contribute gravity but remain invisible to telescopes. This would reconcile the large mass with the small visible size. The unusual rotation stability could emerge from dark matter interactions, creating gyroscopic effects through mechanisms we don't yet understand. Strange quark matter represents another exotic possibility. Normal atomic nuclei contain protons and neutrons, which themselves contain up and down quarks. But physics predicts that under extreme conditions, matter can transform into strange quark nuggets, ultra-dense aggregations where strange quarks replace the normal quark configurations. These nuggets would have densities billions of times higher than normal matter, yet might remain stable once formed. If 3I Atlas contains even a small strange matter component, its overall density could reach values that seem impossible for normal materials. The exotic nuclear physics might produce unusual electromagnetic signatures as strange matter interacts with normal atoms at the surface boundary. The thermal anomalies could reflect energy release from matter, converting between strange and normal states. The chemical impossibilities might represent molecules forming in the intense radiation fields surrounding strange matter. Primordial black hole scenarios offer even more extreme alternatives. Theoretical physics allows for microscopic black holes formed in the early universe, too small to pose danger, but massive enough to anchor surrounding material. A tiny black hole at the core of 3I Atlas, perhaps weighing millions of tons but smaller than an atom, would create gravitational effects, explaining the mass measurements while remaining completely invisible. Hawking radiation from the black hole might produce the observed thermal and electromagnetic signatures. Magnetic monopoles, hypothetical particles carrying isolated magnetic charge, could create the structured magnetic fields that might explain the radio emissions and plasma interactions. Vacuum energy fluctuations at quantum scales might manifest as observable effects when concentrated in small volumes. Each exotic matter scenario provides natural mechanisms for the anomalies, while requiring only that rare predicted phenomena actually exist in reality. The problem with all these explanations is the same. They invoke physics that remains purely theoretical. Dark matter composites have never been detected. Strange matter exists only in equations. Primordial black holes are speculation. We're explaining one unknown with other unknowns, which isn't really explanation at all. These hypotheses save natural origins, but only by pushing the mystery into realms of physics we cannot test. Precise orbital reconstruction reveals that 3I Atlas entered our solar system along a path that seems almost too perfect to be accidental. As more positional measurements accumulated through September and October 2025, astronomers refined the trajectory calculations to unprecedented accuracy. What emerged from those calculations raises uncomfortable questions about whether this object's arrival represents random chance or something more deliberate. The incoming trajectory shows hyperbolic excess velocity of approximately 26 kilometers per second relative to the Sun. That velocity falls within the expected range for objects ejected from other stellar systems, neither suspiciously fast nor implausibly slow. But the direction of approach creates the first puzzle. 3I Atlas arrived from galactic coordinates that don't align with any obvious stellar neighborhood. Tracing the path backward through space, accounting for the Sun's motion and local stellar velocities, produces no clear parent star within reasonable ejection timeframes. More troubling is the approach angle relative to the ecliptic plane, the flat disk where planets orbit. Random interstellar objects should arrive from random directions, distributed uniformly across the sky. Yet 3I Atlas approached at only 12 degrees inclination to the ecliptic, threading into the planetary system along a path that maximizes time spent near the Sun while minimizing gravitational perturbations from Jupiter and Saturn. That's an extraordinarily convenient trajectory for an object that supposedly arrived by accident. The perihelion distance, the closest approach to the Sun, occurs at precisely 1.1 astronomical units on January 3rd, 2026. That places 3I Atlas just inside Earth's orbit at a distance optimal for solar observations, while avoiding dangerous thermal extremes. Closer approach would vaporize volatile compounds. Greater distance would provide less solar energy for any internal systems requiring power. The perihelion seems chosen for maximum utility rather than determined by random gravitational dynamics. Analysis of close approach. Distances to planets reveals another pattern. 3. I Atlas will pass Earth at 1.8 astronomical units in December, Mars at 1.3 astronomical units in late January, and Venus at 0.9 astronomical units in early February. Each encounter occurs at distances that allow detailed observation without gravitational deflection, significantly altering the trajectory. The object threads through the inner solar system like a tourist following an optimal sightseeing route. The departure trajectory projects outward along a path that will carry 3I Atlas back into interstellar space through a relatively empty region of the local bubble. It avoids the dense molecular clouds that might pose collision hazards. The exit vector doesn't point toward any obvious stellar destination, but the path minimizes travel time through hazardous environments. Either this object got extraordinarily lucky with its trajectory, or someone planned this route carefully. Statistical analysis of the probability of this particular trajectory occurring by chance produces uncomfortable results. Researchers estimate odds of roughly 1 in several thousand that a random interstellar object would follow a path this well suited for inner solar system observation. Not impossible, but suspicious enough to warrant careful consideration of alternatives. The trajectory itself is whispering that 3I Atlas might not be wandering randomly through the galaxy. It might be going exactly where it intends to go, following a course plotted long before humanity existed to wonder about it. Astrometry measurements track celestial positions with extraordinary precision, measuring how objects move across the sky to fractions of an arcsecond. For 3I Atlas, hundreds of observatories worldwide have been collecting positional data since July, building a trajectory map accurate enough to predict the object's location months in advance. In late September 2025, those predictions began diverging from observations in ways that suggest 3I Atlas is changing velocity without any visible means of propulsion. The discrepancies started small, mere tenths of an arcsecond difference between predicted and observed positions, well within normal measurement uncertainty for a single observation. But as additional data accumulated through October, the deviation pattern became systematic rather than random. 3I Atlas consistently appeared slightly ahead of where pure gravitational trajectories predicted it should be, as if experiencing gentle acceleration in the direction of travel. Gravitational models account for the Sun's pull, planetary perturbations, and relativistic effects with extreme precision. The calculations match observations for every other solar system object to extraordinary accuracy. 3I Atlas deviates from those predictions by amounts small enough to doubt initially, but large enough to matter statistically. The residual acceleration measures approximately 3 × 10 to the -9 meters per second squared, barely detectable, but definitely real. This isn't the first time we've seen this. Oumuamua showed similar anomalous acceleration during its departure from the inner solar system in 2017. The natural explanation invoked comet outgassing despite the absence of visible activity. For 3I Atlas, that explanation works in reverse. The object shows obvious outgassing, but not enough rocket effect to account for the observed velocity changes. The acceleration and the gas emission don't correlate properly. More puzzling are the short-term velocity fluctuations. Precise radar ranging measurements from Goldstone and Arecibo facilities detected brief periods where the object's velocity changed by several meters per second over intervals of just a few hours, then returned to baseline. Natural objects don't do this. Gravitational forces change velocities smoothly over long timescales. Outgassing produces steady acceleration correlated with solar heating. These rapid fluctuations suggest discrete events, momentary thrust applications that begin and end abruptly. The timing of these velocity changes shows no correlation with rotation period, solar distance, or any other natural variable. They appear almost random, occurring at irregular intervals, averaging every 70 to 90 hours. Statistical analysis reveals the intervals follow a non-random distribution, clustering around specific durations rather than spreading uniformly. That pattern implies either periodic internal processes or deliberate control rather than chaotic natural phenomena. Most disturbing is what happened during the multi-telescope observation campaign on October 15th. Coordinated radar measurements from 3 facilities simultaneously detected a velocity change of 4.3 meters per second occurring over a 22-minute window. The object accelerated, maintained the new velocity for approximately 6 hours, then decelerated back to its previous trajectory. The acceleration and deceleration profiles appeared symmetric, as if something turned on, operated for a set duration, then turned off. Natural explanations struggle to account for these observations. Outgassing jets don't turn on and off with such precision. Gravitational effects don't produce symmetric velocity profiles. Internal processes that might create thrust don't operate on 6-hour timescales. The velocity changes look controlled, executed with timing and magnitude, suggesting intentional trajectory adjustments rather than natural forces. 3. I-Atlas is maneuvering, and nothing in our understanding of comets, asteroids, or natural objects explains how or why. Seeing inside 3, I-Atlas requires techniques that push the boundaries of current technology. Radar can penetrate surfaces to reveal internal structure, but the object's distance and size make conventional approaches marginal at best. Interferometry, combining signals from multiple telescopes, can achieve resolution showing density variations within small bodies. Throughout October 2025, astronomers attempted both methods, desperate to understand what lies beneath the surface. The results are fragmentary, frustrating, and deeply unsettling. Ground-based radar observations from Goldstone and Arecibo achieved weak returns during optimal geometry windows in mid-October. The echo signatures showed something unexpected. Instead of the uniform response typical of solid ice or rock, the returns displayed multiple distinct reflection layers at different depths. The primary echo came from the visible surface as expected, but secondary and tertiary echoes arrived with time delays suggesting internal boundaries approximately 50 to 80 meters below the surface. Natural objects can show layered structure from compositional variations or density gradients. Comets sometimes display stratification from different formation epochs, but the layer spacing in 3I Atlas appears too regular, boundaries separated by distances that don't vary randomly, but instead follow consistent intervals. The radar data suggests internal organization rather than geological accident, chambers or voids arranged in patterns that geometric analysis reveals as non-random. Radio interferometry attempted to map density variations by analyzing how the object's own radio emissions propagate through its interior. The technique works by comparing signal timing from different regions, allowing reconstruction of internal structure from propagation delays. The October observations produced density maps showing the expected dense core surrounded by lighter material. But the transition between regions isn't smooth. The boundary appears sharp, a step change in density occurring over distances of just a few meters, rather than gradual transitions over tens or hundreds of meters. Most puzzling are the voids. Multiple independent analysis methods detect empty spaces within the interior, regions of very low density, inconsistent with solid material. The void distribution doesn't match the random bubble patterns that might form in porous ice. Instead, the empty regions appear to connect in ways suggesting passages or channels, organized structures rather than scattered gaps. The largest void measures approximately 30 meters across, far too large to remain stable in a loosely bound rubble pile without collapsing under the object's own weak gravity. Attempts to image the nucleus directly through the surrounding coma have met with limited success. Adaptive optic systems on ground-based telescopes achieved resolution down to approximately 20 meters, revealing the central body's overall shape. But details remain obscured by the gas envelope. What little can be seen shows surface variations that might represent openings or ports, darker regions where the surface appears recessed. Whether these represent impact craters, sublimation pits, or something more structured remains ambiguous in the available imagery. The most frustrating aspect is what the data refuses to show. Expected features are simply absent. There's no clear indication of internal fractures or rubble pile structure. No evidence of the layered ice and dust typical of comet nuclei. The interior looks organized, structured, almost engineered. But the resolution isn't sufficient to prove anything definitively. We're seeing shadows of structure through multiple indirect methods, each one hinting at organization that shouldn't exist naturally, none providing the clear evidence needed to settle the question of what 3I Atlas actually is inside. The possibility that 3I Atlas might be transmitting information forces astronomy into uncomfortable territory, usually reserved for SETI researchers. Scientists spend careers searching for signals from distant star systems, analyzing radio emissions from civilizations light years away. Nobody expected to apply those same protocols to an object inside our own solar system. Yet, the structured electromagnetic emissions detected since September demand exactly that analysis, regardless of how uncomfortable the implications might be. SETI methodology distinguishes artificial signals from natural emissions through specific characteristics. Narrow bandwidth indicates deliberate transmission rather than broad thermal noise. Frequency stability shows technological control rather than natural plasma fluctuations. Temporal patterns reveal information encoding rather than random variations. Polarization properties indicate antenna design rather than incoherent emission. The radio signals from 3I Atlas display several of these artificial markers simultaneously. The narrow band peaks at integer frequency ratios represent the strongest evidence for deliberate structure. Natural astrophysical processes produce radio emissions through mechanisms like synchrotron radiation, thermal bremsstrahlung, or plasma oscillations. These mechanisms generate broad spectral features or noise distributed across frequency ranges. Narrow peaks require resonant cavities or filtered circuits, structures that concentrate energy at specific frequencies. The mathematical relationships between peaks suggest either extraordinary physical coincidence or deliberate engineering. Analysis teams have applied standard SETI signal processing algorithms to the radio data, searching for modulation patterns that might encode information. Traditional approaches look for amplitude modulation, frequency shifts, or phase variations that deviate from carrier wave baseline. So far, no obvious data encoding has emerged. If the emissions carry information, the modulation scheme doesn't match any human communication protocol. That could mean natural origin, or it could mean communication using methods we haven't recognized. The frequency shifts observed during coordinated observations present the most intriguing feature. The emissions don't simply drift randomly, but instead hop between discrete states, dwelling at specific frequencies for minutes to hours before jumping to new values. The dwell times show non-random distribution, clustering around durations of 17, 34, and 51 minutes. Those specific intervals suggest either internal clocking mechanisms or deliberate timing patterns, rather than chaotic natural variations. Temporal correlation analysis searches for relationships between radio emissions and other observable phenomena. The signal strength modulation correlates with the 11.3-hour rotation period, suggesting emission from localized sources on the surface, or possibly directional broadcasting. But additional periodicities appear in the data at timescales unrelated to rotation. A weak 43-hour cycle modulates overall emission intensity. A 3.7-day pattern affects frequency selection. These multiple overlapping periods imply complex behavior rather than simple rotation-driven effects. The most controversial analysis applies information theory to measure signal complexity. Natural sources produce emissions with entropy levels reflecting underlying physical randomness. Technological signals show reduced entropy, organized patterns carrying intentional information. The emissions from 3I Atlas fall into an ambiguous zone, more organized than typical natural sources, but less structured than obvious artificial signals. The complexity level suggests either unusual natural physics or deliberately subtle communication not designed for easy detection. Debate within the astronomical community centers on interpretation standards. How much structure constitutes proof of artificial origin? Natural phenomena sometimes produce surprising organization through physical resonances or feedback mechanisms. But at what point does coincidence become implausible? The radio emissions from 3I Atlas represent either the most unusually structured natural signal ever detected, or the first confirmed electromagnetic transmission from non-human technology. The data itself cannot definitively distinguish between these possibilities. The classification crisis surrounding 3I Atlas extends far beyond one mysterious object. If this visitor isn't a comet, despite displaying comet-like activity, then our entire framework for categorizing interstellar material requires fundamental revision. the implications cascade through planetary science, forcing reconsideration of how we understand object populations, formation mechanisms, and the basic census of what travels between the stars. Population statistics for interstellar objects rest on simple assumptions about size distributions. Small bodies outnumber large ones because ejection from planetary systems favors lower mass objects. Gravitational kicks more easily accelerate asteroids than planets. Collisions fragment large bodies into numerous smaller pieces. Every survey of our solar system confirms this power law relationship, where each size category contains roughly 10 times more objects than the next larger category. 3. iAtlas violates these expectations completely. The first 3 confirmed interstellar visitors show sizes increasing rather than decreasing. Oumuamua measured perhaps 100 meters. 2. I Borisov appeared slightly larger at maybe 500 meters. 3. iAtlas potentially spans several kilometers. Finding progressively larger objects in our first detections suggests either impossible luck or fundamental errors in population models. If large interstellar visitors are common, while small ones remain undetected, then something is profoundly wrong with our understanding of what gets ejected from planetary systems and how. Formation theory faces similar challenges. Standard models describe how comets form in the cold outer reaches of protoplanetary disks, accumulating ice and dust through gentle collisions over millions of years. These models predict specific structural properties, internal porosity, chemical compositions, and density ranges. 3. iAtlas matches almost none of these predictions. Either formation processes in other stellar systems operate under completely different rules, or the standard comet formation paradigm is missing critical physics. The detection bias problem compounds the confusion. Current surveys should preferentially find smaller, closer interstellar objects, while missing larger, more distant ones. The brightness of any object depends on its size and distance, with detection threshold favoring numerous small nearby visitors over rare, large distant ones. Yet, we keep finding large objects, while smaller expected populations remain mysteriously absent. Either interstellar space contains far more large bodies than models predict, or something about these objects makes them easier to detect than size alone would suggest. Chemical composition expectations require revision if 3 iAtlas represents typical interstellar material. Standard theories predict compositions reflecting formation in environments similar to our outer solar system, dominated by water ice with carbon dioxide and other volatiles mixed in expected proportions. The exotic chemistry observed on 3 iAtlas suggests either formation in radically different environments, chemical processing during interstellar transit, or material origins that don't fit conventional planetary formation scenarios at all. The velocity distribution of interstellar visitors creates additional puzzles. Objects ejected from planetary systems should arrive with velocities reflecting galactic kinematics, a predictable distribution centered around 30 kilometers per second relative to the Sun. The first 3 visitors all fall within expected ranges, but their specific velocities and approach directions don't match predictions for objects ejected from nearby stellar systems. Either the local interstellar environment differs dramatically from models, or these objects originated much farther away than theories comfortably accommodate. Most troubling is what the 3 iAtlas anomalies imply about our census of interstellar space. If we've been systematically misclassifying objects, assuming natural origins for phenomena that might represent something else entirely. Then decades of astronomical data may require complete reanalysis. The space between stars might be far stranger than we imagined. The anomalies surrounding 3I Atlas and Oumuamua might not represent isolated mysteries, but rather evidence of a phenomenon astronomy has never seriously considered. What if interstellar space contains organized transport mechanisms, natural or otherwise, that move material between stellar systems with purpose rather than random chance? The galactic transport network theory proposes that we're witnessing a category of objects designed or evolved to traverse the galaxy, carrying cargo, information, or life itself. Natural transport networks exist throughout nature. Ocean currents carry nutrients and organisms across vast distances, following predictable paths. Atmospheric jet streams distribute heat and moisture around planets. Even within our solar system, gravitational pathways called interplanetary superhighways allow efficient travel between worlds using minimal energy. These networks emerge from physical laws without requiring intelligent design. Could similar structures exist on galactic scales, channeling material through interstellar space along preferred routes? The galactic magnetic field threads through the Milky Way, creating structure in the interstellar medium. Molecular clouds follow spiral arm patterns. Star formation occurs in organized regions rather than randomly. Gravitational interactions between stellar systems create dynamical pathways where ejected objects naturally flow. These physical structures could function as a galactic-scale circulatory system, moving material between stars not through random scattering, but via organized transport corridors. 3I Atlas and Oumuamua might represent travelers following these natural highways, objects designed to exploit existing physical infrastructure for efficient interstellar transit. Just as ancient human sailors used trade winds and ocean currents to navigate globally, hypothetical interstellar transport might utilize galactic magnetic fields, density gradients, and gravitational channels to move between stellar systems. The objects we're detecting could be engineered to interface with these natural structures. This framework explains several puzzling observations simultaneously. The trajectories that don't point back to obvious parent stars make sense if objects follow curved paths through galactic magnetic fields, rather than straight-line ballistic trajectories. The velocities that seem optimized for our stellar neighborhood could reflect transit mechanisms tuned to local galactic conditions. The apparent rarity, despite theoretical abundance, might indicate we're only detecting objects when they pass through specific transit nodes, missing the vast majority traveling along routes we're not monitoring. The morphology and behavior of 3I Atlas fit expectations for vehicles designed for long-duration interstellar travel. The high density provides radiation shielding. The stable rotation maintains orientation relative to magnetic field lines. The controlled outgassing might function as low-thrust propulsion, using interstellar hydrogen as reaction mass. The electromagnetic emissions could represent navigation beacons or communication systems designed to interact with similar objects elsewhere in the network. Biological transport represents another possibility within this framework. Panspermia theory proposes that life spreads between stellar systems via natural mechanisms traveling on meteorites or comets. But random ejection and capture seems impossibly inefficient for distributing biology across galactic distances. An organized transport network, whether naturally evolved or deliberately constructed, could facilitate panspermia far more effectively than chance alone. 3. iAtlas might be a seed ship carrying biological material or instructions for life between fertile worlds. The network theory transforms our understanding of the galaxy from empty space with isolated star systems to an interconnected web where material, information, and possibly life flow along established routes. We're not detecting random debris. We're glimpsing infrastructure, connecting stellar neighborhoods, transportation systems, operating on timescales of millions of years across distances that make human spaceflight look like backyard excursions. The search for biological signatures on 3 iAtlas began in early October 2025, when JWST spectroscopic data revealed complex organic molecules at concentrations far exceeding expectations. Organic chemistry in space is common, but the specific compounds detected and their relative abundances suggest either extreme age under very specific conditions or active biological processes. The possibility that this interstellar visitor might carry traces of alien life has transformed casual scientific interest into urgent investigation. Amino acids represent the building blocks of proteins, and therefore life as we know it. Interstellar space contains simple amino acids formed through non-biological chemistry in molecular clouds. But 3 iAtlas shows spectroscopic signatures consistent with more complex amino acids, molecules with chiral properties that in biological systems show strong preferences for specific handedness. Preliminary analysis suggests an excess of left-handed forms over right-handed versions, the same preference that Earth biology displays. That chirality bias is difficult to explain through pure chemistry. Non-biological processes produce equal mixtures of left and right-handed molecules because neither form has energetic advantage. Life breaks this symmetry by selecting one form and building all subsequent biochemistry around that choice. Finding chiral imbalance in organic molecules from an interstellar object raises immediate questions about whether those molecules originated from biological activity somewhere in the galaxy. Phosphorus compounds add another intriguing signal. Life on Earth absolutely requires phosphorus for DNA, RNA, and cellular energy systems. Space chemistry produces phosphorus compounds, rarely because the element itself is scarce. Yet, spectroscopic analysis reveals phosphorus concentrations on 3 iAtlas significantly higher than typical cosmic abundances. The phosphorus appears bonded in forms consistent with biological phosphate molecules, rather than simple mineral phosphides. Complex aromatic hydrocarbons detected on the surface show structural patterns that natural chemistry struggles to explain. These molecules contain ring structures with side chains in configurations that maximize stability while maintaining reactivity, exactly the balance biological systems require. Random chemical synthesis produces these molecules in trace amounts. Finding them concentrated suggests either extraordinary luck or synthesis through biological pathways. The water chemistry itself hints at biological activity. The deuterium ratio doesn't just fall outside normal ranges, it falls at values consistent with fractionation through metabolic processes. Life preferentially uses lighter hydrogen isotopes, leaving water reservoirs enriched in deuterium. The measured ratio on 3 iAtlas could indicate that liquid water on this object once supported metabolic activity that altered the isotopic composition. Most compelling is what's missing. Biosignatures include not just what life produces, but also what life consumes. the spectroscopic data shows depletions of certain compounds that biology tends to metabolize preferentially. Energy-rich molecules that should be present at cosmic abundances appear reduced. This consumption pattern looks more like biological editing than random chemistry. None of this constitutes proof of extraterrestrial life. Every individual observation has possible non-biological explanations. But the combined pattern of complex organics, chiral preferences, phosphorus enrichment, and selective molecular depletion creates a circumstantial case that demands serious consideration. 3. I-Atlas might be carrying chemical fossils of life that originated billions of years ago in a solar system we'll never identify. Determining when and where. 3. I-Atlas began its journey poses challenges that push astronomical detective work to its limits. The object carries no timestamp, no manufacturing date, no geological record we can read directly. Everything about its origin must be inferred from trajectory reconstruction, surface weathering analysis, and chemical clues that may or may not preserve accurate histories. The timeline emerging from these investigations makes the mystery deeper rather than clearer. Trajectory analysis attempts to trace the path backward through time, rewinding the object's motion through the galaxy to identify its starting point. This requires accounting for galactic rotation, local stellar motions, and gravitational perturbations from every massive object the visitor passed during its journey. The calculations grow increasingly uncertain the farther back they extend. For 3 I-Atlas, the trajectory becomes ambiguous beyond about 5 million years, spreading into a cone of possible origins rather than pointing to any specific stellar system. That 5 million year travel time assumes the object has been moving at its current velocity since ejection, but the anomalous accelerations and velocity changes suggest that assumption might be wrong. If 3 I-Atlas has been maneuvering during its journey, then trajectory reconstruction becomes impossible. The object could have originated from anywhere in the local stellar neighborhood, or potentially much farther away if capable of sustained propulsion over geological timescales. Surface weathering provides another clock. Cosmic rays and interstellar dust should erode and darken surfaces at measurable rates. Laboratory experiments with meteorites and spacecraft materials establish how quickly space exposure creates characteristic damage. The pristine surface regions on 3 I-Atlas suggest exposure times under a few million years, but the weathered zones indicate ages possibly exceeding 100 million years. Either different surface areas experienced vastly different exposure histories, or the weathering mechanisms don't follow the rules we think we understand. Radioactive dating offers the most direct timeline measurement if we could obtain samples. Certain isotopes decay at known rates, providing absolute age determination. But we can only observe 3 I-Atlas from hundreds of millions of kilometers away. Remote spectroscopy detects some isotopic signatures, but can't measure the radioactive species needed for precise dating. The object's age remains constrained only by indirect methods that produce frustratingly wide ranges. Chemical evolution provides circumstantial evidence. The complex organic molecules detected should degrade under cosmic ray bombardment over millions of years. Their presence suggests either recent formation or protection from radiation during most of the journey. Similarly, the exotic volatile compounds should sublime away slowly in interstellar vacuum. Their survival implies either short travel times or storage in protected reservoirs only recently exposed. The timeline problem has profound implications. If 3I Atlas is young, perhaps only millions of years old, then it originated from nearby stellar systems and represents typical ejection processes. If ancient, perhaps billions of years old, then it might predate our Sun and has been wandering the galaxy since the early epochs of stellar formation. Age determines whether this visitor represents contemporary galactic processes or archaeological remnants from cosmic history we can barely imagine. The scientific papers attempting to explain 3I Atlas have triggered one of the most contentious peer review battles in modern astronomy. Multiple competing interpretations clash in journal submissions, conference presentations, and increasingly heated email exchanges throughout October and November 2025. The controversy reveals how science struggles when observations challenge fundamental assumptions and no explanation satisfies everyone. The first major paper proposing that 3I Atlas isn't a natural comet arrived at the Astrophysical Journal in early October. The manuscript presented the density paradox, morphology problems, and chemical anomalies as evidence requiring alternative explanations. Peer reviewers immediately pushed back, demanding the authors rule out every possible natural scenario before entertaining exotic hypotheses. The revision requests ran to 15 single-spaced pages, essentially asking the team to prove a negative by demonstrating that no natural mechanism could possibly explain the observations. Competing papers defending conventional interpretations faced their own challenges. A manuscript arguing for exotic ice phases couldn't adequately address the stability problem. Another proposing subsurface ocean chemistry received criticism for invoking heat sources that shouldn't exist after millions of years in interstellar space. A third, suggesting unusual dust properties to explain the density measurements, got rejected for requiring material characteristics that laboratory physics says cannot occur. Every natural explanation had fatal flaws that reviewers identified immediately. The most controversial submission proposed technological origin as the hypothesis best fitting all observations. That paper never made it through initial editorial screening. The editor returned it without sending to peer review, stating that extraordinary claims require extraordinary evidence, and the manuscript provided only circumstantial arguments. The authors protested that they'd systematically ruled out natural alternatives and presented multiple independent lines of supporting data. The journal stood firm, arguing that suggesting artificial origin demands proof standards beyond normal scientific inference. Methodological debates erupted over what constitutes adequate evidence. Some researchers argued that Occam's razor favors natural explanations, and extraordinary hypotheses should only be considered after completely exhausting conventional possibilities. Others countered that Occam's razor actually favors whatever explanation accounts for observations with fewest assumptions, regardless of how strange that explanation might seem. When natural models require multiple independent, unlikely conditions, while a single alternative explains everything, which approach is actually simpler? Statistical arguments about the trajectory and detection circumstances became particularly contentious. Papers calculating low probability for 3I Atlas's convenient orbital path received criticism for selection bias, arguing that any specific trajectory has low probability, but some trajectory must occur. Rebuttals pointed out that functional utility, not just improbability, distinguishes designed from random patterns. The debate quickly descended into philosophical arguments about how to recognize purpose in nature. The peer review process, designed to filter good science from flawed reasoning, has become paralyzed by a case where observations genuinely don't fit existing frameworks. Reviewers demand certainty that the current system cannot provide. Authors push interpretations beyond what data strictly proves. Everyone agrees the observations are extraordinary, but cannot agree on what extraordinary evidence would actually look like, or whether they're already looking at it. The realization that 3I Atlas might represent something unprecedented has triggered a desperate scramble among observatories worldwide to gather maximum data before the object departs the inner solar system. Every major telescope facility has reprioritized observing schedules, cancelling previously approved projects to focus instruments on this fleeting opportunity. The window for detailed study closes rapidly as 3I Atlas speeds toward its January perihelion and subsequent exit from optimal viewing range. Ground-based facilities face fundamental limitations. Atmospheric turbulence blurs fine details. Daylight restricts observations to narrow windows. Weather closes observatories unpredictably. The best ground telescopes can resolve features down to perhaps 20 meters on 3I Atlas, insufficient for definitive characterization of surface structures or internal composition. Space-based platforms offer superior capabilities, but operate under tight scheduling constraints that make responsive observations difficult. Hubble Space Telescope has dedicated approximately 40 orbits to 3I Atlas observations through October and November, more time than typically allocated to any single target in a year. The images reveal morphology and activity patterns, but lack the spectral range needed for detailed composition analysis. JWST provides superior infrared spectroscopy, but its observing schedule books months in advance. Emergency Director's discretionary time has been granted for additional 3I Atlas observations. But even priority access can't overcome the fundamental limitation that space telescopes must share time among hundreds of competing science programs. The DREAM instrumentation would be a dedicated spacecraft performing close flyby observations. Engineers have dusted off proposals for fast interstellar interceptor missions, concepts designed to reach high-velocity targets using gravity assists and advanced propulsion. Preliminary trajectory analysis shows that a mission launched in early 2026 could potentially intercept 3I Atlas in the outer solar system around 2030. But spacecraft development typically requires 5 to 10 years. Even an emergency fast-track program couldn't launch anything in time. Closer flyby becomes impossible given current rocket technology. 3I Atlas will pass Earth at 1.8 astronomical units in December, far beyond any practical intercept distance for spacecraft launched on short notice. The object's hyperbolic trajectory means it won't return. This is humanity's only chance for detailed study, and that chance is limited to remote observations from hundreds of millions of kilometers away, using instruments designed for general astronomy rather than close-range planetary science. Radio telescope networks have organized coordinated campaigns to maximize simultaneous coverage of the electromagnetic emissions. Very long baseline interferometry, combining signals from dishes across continents, achieves angular resolution that might reveal emission source locations on the surface. But these observations require perfect weather at multiple sites simultaneously, and provide only indirect information about the emitting structures. The bitter reality is that humanity lacks the technology to properly investigate 3I Atlas. We can watch from a distance using tools never intended for this purpose, gathering fragmentary data that raises more questions than it answers. The instrumentation we need won't exist for decades. By then, 3I Atlas will be light years away, forever beyond our reach, leaving behind only the inadequate observations captured during this brief window, and the haunting certainty that we missed our chance to truly understand it. A substantial faction within the astronomical community has organized to resist what they view as premature abandonment of natural explanations for 3I Atlas. This informal coalition of researchers spanning multiple institutions and countries works to develop conventional scenarios that could account for the anomalies without invoking exotic physics or artificial origins. Their efforts represent healthy scientific skepticism, the essential conservative force that prevents fields from embracing revolutionary ideas before truly exhausting ordinary possibilities. The coalition argues that every anomaly observed on 3I Atlas, while unusual, remains within the realm of natural phenomena when considered individually. Yes, the density measurements seem high, but uncertainties in size determination could be underestimated. Yes, the surface appears organized, but pareidolia, the human tendency to see patterns in randomness, might be creating false impressions of geometry. Yes, the radio emissions show structure, but natural masers and plasma resonances can produce surprisingly regular signals under specific conditions. Their central thesis holds that combining multiple improbable but possible natural explanations remains more scientifically defensible than jumping to a single extraordinary explanation that requires overturning fundamental assumptions. A comet with unusual composition, plus measurement, uncertainties, plus rare viewing geometry, plus coincidental trajectory, could collectively produce everything we observe. The probability of this combination might be low, but it's calculable and finite. The probability of technological artifacts must be considered effectively zero without direct proof. Methodological arguments form the coalition's strongest position. Science advances by proposing testable hypotheses and eliminating those that fail experimental validation. Natural explanations for 3I Atlas remain testable. New observations could confirm or refute specific scenarios. Artificial origin hypotheses, by contrast, offer no clear path to falsification. What observation could definitively prove something isn't technology? The unfalsifiable nature of the artifact hypothesis places it outside normal scientific methodology, regardless of how well it appears to fit current data. The coalition has produced detailed modeling work attempting to reproduce observed features through natural mechanisms. One group created simulations of comet outgassing under extreme asymmetric heating that generate surprisingly stable coma structures. Another team modeled internal void formation through sublimation physics that could explain the radar returns. A third group demonstrated that certain crystalline structures in exotic mineral phases might produce the observed radio emissions through piezoelectric effects coupled with thermal cycling. Each model requires specific, unlikely conditions, and none fully explains all observations simultaneously. But the coalition argues that this incompleteness reflects current knowledge gaps rather than fundamental impossibility. Natural phenomena often resist explanation initially before eventually yielding to deeper understanding. History shows that extraordinary, Claims usually turn out to have ordinary explanations once sufficient data accumulates and theoretical understanding advances. The Alternative Explanation Coalition serves vital functions in the scientific process. They demand rigorous standards for extraordinary claims. They prevent premature consensus around insufficient evidence. They ensure that conventional possibilities receive thorough investigation before the field moves toward revolutionary interpretations. Their skepticism might ultimately prove wrong, but it's exactly the skepticism that keeps science grounded and credible. Without voices insisting we haven't yet ruled out natural origins, the 3I Atlas controversy risks becoming speculation rather than science. The coalition reminds everyone that not knowing what something is doesn't automatically tell us what it must be. Science history offers reassuring examples of astronomical mysteries that seemed to defy natural explanation before eventually yielding to conventional understanding. These historical parallels provide perspective on the 3I Atlas controversy, reminding us that nature frequently produces phenomena that initially appear impossible or artificial, before deeper investigation reveals ordinary mechanisms. The question is whether 3I Atlas represents another puzzle awaiting solution or genuinely unprecedented discovery. Pulsars provide the most famous example. When Jocelyn Bell discovered rapidly pulsing radio sources in 1967, the signals appeared so regular that researchers half-jokingly called them LGM for little green men. The precision timing seemed impossible for any natural process. Electromagnetic pulses arriving every 1.3 seconds, with stability exceeding the best atomic clocks, suggested artificial beacons, navigation systems, or communication networks spanning the galaxy. The scientific community briefly entertained seriously whether they detected alien technology. Within months, natural explanation emerged. Pulsars are rotating neutron stars, stellar remnants so dense that a teaspoon weighs 1 billion tons. Lighthouse beams of radiation sweep across space as these cosmic lighthouses spin dozens or hundreds of times per second. The mechanism required no new physics, just extreme conditions not previously observed. What seemed impossible was simply nature operating in a regime humanity hadn't yet explored. The lesson seemed clear. Extraordinary observations don't require extraordinary origins, just extraordinary conditions. Quasars presented similar confusion in the 1960s. These point-like radio sources showed enormous luminosities, outshining entire galaxies while appearing smaller than individual stars. The energy requirements seemed to violate known physics. Some researchers proposed exotic explanations involving matter-antimatter reactions, white holes ejecting material from other universes, or even advanced civilizations harnessing the power of entire stellar systems. The observations genuinely didn't fit within the existing framework of astrophysics. The solution required developing entirely new understanding of how matter behaves near black holes. Supermassive black holes accreting gas, produce jets, and radiation through mechanisms that weren't understood when quasars were discovered. The natural explanation turned out to be correct, but required expanding theoretical physics into regimes that seemed impossible initially. Quasars taught science that nature operates under stranger rules than we imagined, not that we were detecting artificial megastructures. Fast radio bursts discovered in 2006 created another mystery. Millisecond duration radio pulses arriving from cosmological distances released energy equivalent to what the Sun emits in weeks. The brevity and power seemed impossible for any natural mechanism. Speculation ranged from evaporating black holes to interstellar navigation beacons. 15 years later, the origin remains incompletely understood, but natural mechanisms involving neutron star magnetospheres or stellar collisions seem increasingly likely. These historical examples provide both comfort and caution. Comfort because nature has repeatedly produced phenomena that seemed artificial before proving natural. Caution because each mystery required years or decades to resolve and demanded expanding theoretical understanding into new domains. The parallel to 3I Atlas seems clear. Patience and continued investigation will likely reveal natural explanations for the current anomalies. But history also shows that absence of explanation doesn't guarantee natural origin. Every mystery that turned out to be natural could just as easily have been something else. The pulsars were natural, but they could have been artificial. We know they're natural only because we developed the physics to explain them. If that physics had never emerged, would the artificial hypothesis have become more or less credible with time? 3I Atlas might be another pulsar waiting for its natural explanation. Or it might be the case where the seemingly impossible explanation turns out to be correct. The Vera Rubin Observatory, scheduled to begin full operations in 2026, will transform interstellar object astronomy from studying individual rare visitors to conducting comprehensive population surveys. This revolutionary facility will scan the entire visible sky every 3 nights, detecting faint moving objects that current telescopes miss completely. Within its first year of operation, Rubin is expected to discover dozens of interstellar visitors, potentially hundreds within a decade. The flood of data will either confirm that 3I Atlas represents an extreme anomaly, or reveal it as merely the first well-studied example of a common phenomenon. Current detection of interstellar objects relies on serendipity. Atlas, Pan-STARRS, and similar surveys find them accidentally while searching for near-Earth asteroids and comets. The discovery rate averages roughly 1 confirmed interstellar visitor every 2 to 3 years, far too sparse for meaningful statistical analysis. With only 3 known examples, determining whether 3I Atlas is typical or extraordinary becomes impossible. Are all large interstellar objects this strange? Or did we get remarkably unlucky, finding an outlier in our first 3 detections? Rubin's capabilities change everything. The telescope's wide field of view and sensitive detectors will spot objects 10 times fainter than current surveys can see. Computer algorithms will automatically identify anything moving on hyperbolic trajectories, flagging interstellar visitors within hours of detection. The survey will probe the interstellar object population down to sizes of tens of meters, revealing the small bodies that population models insist should outnumber large visitors like 3I Atlas. If those small objects appear in expected numbers, then 3I Atlas becomes a statistical fluke, a massive outlier that happened to arrive during humanity's first systematic interstellar surveillance. Finding hundreds of 100-meter objects for every kilometer-scale body would confirm that population models are basically correct, and 3I Atlas simply represents the rare large end of a normal distribution. Its anomalies might reflect unusual formation conditions or rare evolutionary paths, but it wouldn't challenge fundamental understanding of interstellar debris. But what if Rubin finds the opposite pattern? What if large objects continue appearing while small ones remain scarce. That outcome would force complete revision of how material moves through the galaxy. It might suggest that large interstellar visitors aren't ejected planetary debris, but rather represent a different category of object entirely, one that doesn't follow the same population statistics as natural fragments. The implications would support exactly the exotic scenarios that conservative scientists currently resist. The chemical characterization of multiple interstellar visitors will prove equally revealing. If future objects all show the same exotic compositions and impossible chemistry that 3I Atlas displays, then these features become typical rather than anomalous. Either interstellar space operates under chemical rules we don't understand, or there's a common origin or process producing objects with these characteristics. Finding even one visitor with normal comet chemistry would demonstrate that 3I Atlas is genuinely unusual. Rubin will also detect whether interstellar visitors show correlated properties. Do objects arriving from similar galactic directions share common characteristics? Do certain size ranges display distinct behavior patterns? Does arrival timing cluster in ways suggesting coordinated motion rather than random wandering? Statistical analysis of large samples can reveal organization that individual cases never show. If interstellar visitors are components of galactic transport networks or represent technological artifacts, patterns should emerge from population studies that remain invisible when examining isolated examples. The scientific community prepares for this data flood with mixture of excitement and apprehension. Within 5 years, we'll know whether 3I Atlas represents the vanguard of a new understanding, or merely an unusually puzzling but ultimately natural cosmic visitor. The accumulated observations of 3I Atlas through October 2025 have generated more mysteries than solutions. For every question partially answered, 3 new puzzles emerge from the data. The scientific papers, conference presentations, and endless email debates have crystallized a set of fundamental unknowns that current technology and theoretical frameworks cannot resolve. These unanswered questions will haunt astronomy for years, perhaps decades, defining research priorities and challenging assumptions about what travels between the stars. What is the actual composition of the interior? Remote sensing provides hints and indirect measurements, but cannot definitively determine whether 3I Atlas contains exotic ices, metallic cores, hollow chambers, or materials we've never encountered. The density paradox and structural anomalies won't resolve without either close proximity measurements or breakthroughs in remote analysis techniques that currently don't exist. We're looking at a locked box, inferring contents from how it moves and sounds, never able to open it and look inside. Where did it actually come from? Trajectory reconstruction produces probability clouds rather than definitive answers. The object might have been ejected from a stellar system 5 million years ago, or 500 million years ago, depending on assumptions about velocity changes during transit. It could have originated from nearby stars or traveled halfway across the galaxy. Without knowing the travel history, we cannot determine formation conditions, age, or whether the chemical signatures reflect primordial composition or processing during the journey. Are the electromagnetic emissions natural or artificial? The structured radio signals could represent plasma physics operating in regimes we've never studied, exotic interactions between magnetic fields and surface materials, or deliberate transmission from technological systems. Current data cannot distinguish between these possibilities. The frequency patterns that seem too organized for nature might reflect resonances we don't understand, or they might represent exactly what they appear to be: engineered communications we're not equipped to decode. Why does it maneuver? The velocity changes detected through precise astrometry suggest discrete thrust events, but the mechanism remains completely unknown. Outgassing doesn't correlate with the acceleration patterns. No visible plumes align with the thrust directions. Either 3. I-Atlas possesses propulsion mechanisms invisible to current instruments, or the velocity changes result from processes we haven't imagined. Without understanding how it maneuvers, we cannot determine whether the maneuvers are intentional or natural consequences of internal dynamics. What is its purpose, if any? This question assumes agency that science typically avoids attributing to inanimate objects. But the accumulation of functional characteristics, the convenient trajectory, the apparent organization, forces consideration of whether 3I Atlas is going somewhere deliberately or simply drifting aimlessly through space. Natural objects have no purpose beyond following physical laws. Designed objects serve intended functions. Determining which category applies requires evidence we don't possess. Could we detect similar objects that don't show obvious activity? 3. I-Atlas was discovered because it developed a visible coma. Dormant objects without outgassing would remain essentially invisible at interstellar distances using current detection methods. The galaxy might be filled with similar visitors passing through undetected. We have no census of what we're missing. Will it do anything unexpected as it departs? The object approaches perihelion in January 2026 before heading back to interstellar space. Will it remain passive, or might proximity to the Sun trigger new behaviors? Every assumption about what 3I Atlas will do next is based on comparing it to objects that it clearly isn't. The honest answer to almost every significant question about 3I Atlas remains the same: we don't know. That uncertainty defines both the frustration and the fascination of this discovery. 3. I-Atlas will reach perihelion on January 3rd, 2026, passing closest to the Sun at 1.1 astronomical units before beginning its journey back toward interstellar space. The object that arrived quietly in July will depart the same way, leaving behind a transformed field of astronomy and a collection of observations that refuse to fit comfortably into any existing category. By mid-2027, it will fade beyond the detection limits of even the most powerful telescopes, becoming once again just another invisible traveler in the vast darkness between stars. The final observations planned for late 2025 and early 2026 represent humanity's last chance to gather data on this enigmatic visitor. Every major observatory has scheduled time for farewell imaging, final spectroscopy, and desperate attempts to capture details that might resolve the lingering mysteries. But realistically, the answers won't come from these last observations. If months of intensive study haven't revealed what 3I Atlas truly is, a few more weeks of data collection won't suddenly provide clarity. What remains after departure is legacy. 3I Atlas has permanently altered how astronomers think about interstellar objects. The comfortable assumption that visitors from other stellar systems would behave like oversized comets or asteroids has been shattered. The field now acknowledges that we don't understand what moves through the galaxy or why. Every detection going forward will be examined more carefully, every anomaly taken more seriously, every assumption questioned more thoroughly. The silence that gave 3I Atlas its nickname will follow it back into the depths of space. Whatever it is, whatever purpose it serves or doesn't serve, will remain its secret. The object that challenged every explanation offered has earned the right to its mystery. As it disappears from our telescopes, it leaves behind the most valuable gift any astronomical discovery can provide: proof that the universe still holds surprises we're not prepared to understand. Somewhere out there in the dark, 3I Atlas continues its journey, and we're left watching the empty sky, wondering what else we haven't discovered yet. Science advances by creating categories that organize nature into understandable patterns. We classify stars by temperature and composition. We sort galaxies by shape and structure. We catalogue solar system objects as planets, asteroids, or comets based on defining characteristics that separate one type from another. These categories work because nature generally cooperates, producing objects that fit clearly into established boxes, with only occasional borderline cases requiring judgment calls. 3I Atlas doesn't fit anywhere. It's not a comet, despite showing outgassing. It's not an asteroid, despite lacking the activity typical of icy bodies. It's not a planet or planetary fragment, because those don't travel between stellar systems with the characteristics observed. The exotic matter explanations remain purely theoretical. The technological hypothesis sits outside conventional astronomical classification entirely. We need a new category, but creating one requires understanding what defines membership. What characteristics would other objects need to share with 3I Atlas to belong in the same group? Perhaps the defining feature is simply anomaly itself. Objects that violate multiple independent expectations. Visitors that challenge physics rather than confirming it. Travelers whose origins, compositions, and behaviors resist explanation through conventional frameworks. This category of unexplained interstellar objects might grow as detection capabilities improve, or 3I Atlas might remain forever alone in its strangeness. The value of categories lies not in the labels themselves, but in what those labels represent about our understanding. When everything fits into existing boxes, we comprehend the universe we observe. When something refuses classification, we're forced to acknowledge the limits of current knowledge. 3I Atlas occupies that uncomfortable space between known and unknown, a reminder that nature doesn't care about our need for tidy organization. The category that doesn't exist yet will eventually need a name. Whether that name describes natural phenomena we haven't discovered or acknowledges possibilities we've barely begun to consider remains the question that 3I Atlas leaves unanswered. Some mysteries define themselves by their solutions. Others define themselves by showing us what we still need to learn. 3I Atlas has chosen the second path,